Martin Jähnert from the Max Planck Institute of the History of Science. And he is now, however, finishing his PhD at the Technische Universität in Berlin with tutors Jürgen Renn and Friedrich Steiner. And I give you the floor.
Okay, thank you very much, and thank you for having me. I'm very happy to present my work, my PhD work here today. As many of you know, I'm studying the applications of the correspondence principle in the old quantum theory, and doing so, I'm analyzing the principle as a research tool and its integration and adaptation in various research fields in the 1920s. What I'm going to present today is one of my case studies, and I will do this in particular by focusing on its relation to Heisenberg's Umdeutung. I want to start my talk by going to its end. Consider this quote taken from Wolfgang Pauli's Handbuch article from 1925, which was famously outdated by the time of its publication. In it, Pauli addresses the intensity formulas for the Zeeman effect, which had recently been proposed by Helmut Höhnel and Ralf Kronig. And he connects them directly with a search for a new quantum kinematics. Burdened with the wisdom of hindsight, we can hardly miss the connection between Pauli's statement and Heisenberg's famous 1925 paper. As the reference to the yet unknown quantum kinematics suggests, however, this statement was written before Pauli actually received Heisenberg's work. It thus formulates an expectation for upcoming development, and what is more important, it suggests where this development is going to come from, namely from the specific problem of determining intensities for the Zeeman effect. How did Pauli come to this position in which the problem of determining intensities appeared as the key to a new quantum kinematics? What were the lessons which he thought could be learned from this problem, and most importantly, how did these lessons feed into Heisenberg's work on Umdeutung? To answer these questions, I will reconstruct the development of what I call the intensity problem in the old quantum theory. Taking off in 1922, I will introduce the problem and Arnold Sommerfeld's and Werner Heisenberg's approach to it on the basis of the original correspondence principle. In the second part of my talk, I will follow the development of the problem from 1923 until 1924 and show how it was reformulated within Sommerfeld's Gesetzmäßigkeiten approach. In the last part, I will discuss how Sommerfeld's new formulation of the intensity problem became a challenge for the correspondence approach, and how the attempts to resolve it fueled Heisenberg's work on Umdeutung. This reconstruction will leave many aspects of a much more complicated and detailed story aside. For example, I will not discuss Heisenberg's and Sommerfeld's work in detail based on Kramer's Zwischenbahn. Also, I will not follow Bohr's and Heisenberg's arguments on the sharpening of the correspondence principle. I'm doing this mostly to stay in time, but more importantly, to keep the focus on the main point of my reconstruction. The intensity problem emerged and developed within Arnold Sommerfeld's work on multiplet spectra in the 1920s. To understand its formulation, it's necessary to consider it as part of this approach and more generally. This approach has recently been characterized by Suman Seth, who has argued that Sommerfeld aimed to formulate semi-empirical regularities, or Gesetzmäßigkeiten, to describe the structure of multiplets. Doing so, Sommerfeld used spectroscopic term schemes, which we saw yesterday, and which you can see here in the case of composite doublets and triplets. And the central idea of his approach was to interpret this representation based on spectroscopic terms and Ritz combination principle in terms of transitions between stationary states. Or in other words, he tried to translate the traditional classification of spectroscopy into the language of quanta. This translation was at the heart of Sommerfeld's Gesetzmäßigkeiten approach. The first major advance of it was the description of doublets and triplets on the basis of the inner quantum number, which simply labeled the different states without initially having a definite meaning. Now, the intensity problem, as I will discuss it, emerged within this general description. Before going on with the story, let me briefly introduce the problem more abstractly. In a broad sense, the intensity problem is the task of determining intensities of spectral lines in general in the Bohr model. For the purpose of our talk, the intensity problem has a more narrow and specific formulation. It denotes the task of finding the relative intensity of a set of transitions with the same initial or the same final state. The term scheme which you see here represents the latter scenario as all the lines end on the same level. Now, in 1922, Sommerfeld's first approach to the intensity problem was a qualitative one. It took off from a qualitative description customary in spectroscopy, which distinguished between intense main lines and weaker satellites. In the new description based on the inner quantum number, these strong lines corresponded to transitions in which the azimuthal and the inner quantum number changed in the same sense, i.e. by +1, -1, or 0. Weaker lines then instead corresponded to transitions in opposite senses. This observation was formulated by Sommerfeld in this qualitative intensity rule, which you see here. It cast the intensity problem in a particular form and called for a theoretical description accounting for the apparent correlation between the azimuthal and the inner quantum number. Now, approaching this task, Sommerfeld and Heisenberg would eventually turn to the correspondence principle. Now, but before discussing their work, let me briefly introduce Bohr's original formulation of the principle. In the Bohr model, as all of you know, the motion of an electron is no longer the source of radiation. This separation is addressed by the correspondence principle. Its core idea is that there is some causal connection between the electron's motion and its radiation. More precisely, the principle states that the Fourier coefficients and frequencies of the electron's motion are associated with the transition probabilities and transition frequencies. This core of the principle suggests that transition probabilities should be determined in some way by the Fourier coefficients of the atomic motion. As such, the principle presents a central tool in the old quantum theory for the discussion of intensities in the Bohr model. Applying this tool meant, in general, to find a Fourier representation of the atom and to associate it with the radiation of a set of its transitions. Now, there would be a lot to say about this approach and its problems, and I will not do it here. I just want to stress one aspect which is essential for a story. As you can see from these two quotes, Sommerfeld and Heisenberg understood the correspondence principle as a statement about the kinematics of the atom. You cannot say if you don't let us try already. Okay. This had two important implications for their work. On the one hand, it allowed them to sidestep dynamical problems as encountered in the treatment of multi-electron atoms and the anomalous Zeeman effect. On the other hand, making correspondence arguments meant to adopt a physical interpretation of the multiplet atom and thus to go beyond Sommerfeld's formal interpretation of spectroscopic classifications. Such an interpretation only emerged gradually in the fall of 1921, following a debate between Heisenberg and Landé. Following them, the motion of the multiplet atom was described in this processional form, which we discussed also yesterday. And the inner quantum number was interpreted as the total angular momentum of the atom. So in this description, there was first the description of Sommerfeld's theory of the fine structure, in which the electron moves around the nucleus on an elliptic orbit. On top of this, the plane of the electronic orbit precesses around the axis of the total angular momentum, and finally, the entire atom precesses around the axis of an external magnetic field in the case of the Zeeman effect. The relation between these precessional motions is described through the angle between the different momenta. For Sommerfeld, Heisenberg, and Landé, these angles were space quantized, and we've heard yesterday what this meant. On the basis of this general kinematic description, Heisenberg developed a first correspondence argument in November 1921 by setting up a generic Fourier representation of the kinematics just described. Together, Sommerfeld and Heisenberg then developed this correspondence argument into an account for the intensity distribution of multiplets in the Zeeman effect. This argument was quite straightforward. Sommerfeld and Heisenberg started out with the precessing elliptic orbit of the electron and described it by this generic Fourier representation. By means of a simple coordinate transformation, they then introduced a rotating frame of reference which described the precessing ellipse precession of the orbital plane around the axis of the total angular momentum. And they would also do a similar coordinate transformation in the case of the Zeeman effect. Now this leads to the following Fourier representation, which you see here, and the Fourier coefficients which determine the transition probabilities. They consist of the Fourier coefficient AS of the initial ellipse and these trigonometric terms. The former are the same for a particular multiplet and thus drop out from an intensity ratio, while the latter accounts for the intensity distribution of the different components. Now, the Fourier representation just developed in itself describes a purely classical system and does not yet contain a quantum theoretical assumption. Sommerfeld and Heisenberg introduced such assumptions when they identified the angle in the correspondence formulas with the angles between the axes of the different momenta. This interpretation establishes a connection between the classical Fourier representation and the idea of space quantization. Consequently, the intensity distribution becomes a direct expression of the inclination of the electronic orbit with respect to the total angular momentum. This interpretation provides the key to interpret the correlation expressed in Sommerfeld's qualitative intensity rule. For small angles between the respective momenta, the correspondence formulas show this marked asymmetry, which you see here, and thus suggest that the distinction between mainlines and satellites is just a manifestation of the different spatial configurations of the atom. At this point, we'll have to leave Sommerfeld and Heisenberg and turn to the reformulation of the intensity problem in the years of 1923 and 1924. This reformulation takes us away from the correspondence principle and the kinematics of the atom and deeply into Sommerfeld's Gesetzmäßigkeiten approach. In September 1923, Sommerfeld returned to the intensity problem in reaction to a talk given by Leonhard Ornstein at the Deutsche Physikertage in Bonn, titled Über photographische Photometrie. In it, Ornstein discussed new results on the intensities of multiplets made by his group in Utrecht and caught Sommerfeld's attention. The main result of the ensuing collaboration was the formulation of the so-called Utrecht sum rules and the attempt to establish intensity schemes like the ones you see here. These schemes recast the intensity problem in a new and strikingly different way, as they determined the intensity of the individual components in terms of quantum numbers within Sommerfeld's formal Gesetzmäßigkeiten approach. To show you how Sommerfeld's approach worked, I will walk you through the construction of the simplest possible case. First, one takes the inner quantum numbers of the initial and the final state and uses them as the rows and columns of an intensity scheme. The transitions between them are then characterized by the fields in between. Then one introduces the selection rule, sets the unobserved transition to 0, and likewise assigns non-zero transition probabilities to the other transitions. The actual intensities for these transitions are then determined on the basis of the so-called Utrecht sum rules, which unfortunately I cannot discuss here in more detail. According to these rules, the total intensity of the transitions involving the same initial state is proportional to the statistical weights associated with the final state, and vice versa. Translated into the intensity schemes, these rules imply that the total intensity of a particular row is proportional to the statistical weight associated with the columns, and vice versa again. Taken together, these relations provide a system of linear equations which determines the intensity of the individual components. Now, this approach leads to a complete solution in the simplest possible case of the so-called composite doublets, which I've just shown you. For every case which is more complicated, the system of linear equation becomes underdetermined and makes it necessary to introduce additional assumptions. Though this issue of the underdetermination remained an open question, Sommerfeld hoped that he could formulate a theory of intensities which determined the intensities from arithmetic relations like the Utrecht sum rules. Such a theory would be based on intensity schemes and would no longer make use of atomic models or correspondence arguments. Now, from this position, Sommerfeld launched his famous attack against the correspondence principle in September 1924. In private letters to Kramers and Bohr and his influential lecture at the Versammlung Deutscher Naturforscher und Ärzte in Innsbruck, he argued that the correspondence principle was both inadequate as a foundation for quantum theory and ill-suited to describe the simple arithmetic relations formulated by the Utrecht sum rules. Now, as I'm showing in my dissertation, Sommerfeld's hope for a future theory of intensities did not pan out in the way that he had expected, and he soon returned to the correspondence principle and adapted it in order to solve his problem. This, however, is subject of another discussion. For the purpose of this talk, I will now turn to the reaction to Sommerfeld's approach in Copenhagen. This reaction took place in two stages in September 1924. Initially, Bohr, Kramers, and Heisenberg argued that the sum rules were consistent in principle with the correspondence approach and defended the correspondence principle on a general level without, however, touching on the issues raised by Sommerfeld. These arguments are not essential for my reconstruction, and I will instead focus on the constructive responses developed in a second stage by Heisenberg, Pauli, and Kronig. They searched for a connection between Sommerfeld's formal intensity schemes and the correspondence approach. These attempts, I will now show, played a huge role on Heisenberg's pathway to Umdeutung. Now, the development unfolded in January 1925 when Ralph Kronig arrived in Copenhagen and developed the intensity formulas for the Zeeman effect, which Pauli would later comment on in his Handbuch article. Kronig found these formulas from the observation that the intensities of the Zeeman components could be described by quadratic functions of the magnetic quantum number m. Pursuing this observation, he took quadratic equations of the most general form and then determined the coefficients alpha, beta, and gamma using the sum and polarization rules. Doing so, he introduced a consideration that became tremendously important, as Kronig assumed the sum and polarization rules not only held in cases where all transitions were observed, but also at the so-called edges of the schemes, which you see here as the dotted lines. Here, one or two transitions are not observed. The reason for this was not that the transitions were forbidden by the selection rules, but because the respective states in the lower levels did not exist. The implication of this assumption was that the intensity formulas needed to vanish at the edges for these virtual components. Now, these vanishing intensities then provided the zeros for Kronig's quadratic equations and as he showed, made it possible to determine the coefficients. Now, obviously, this solution was no longer based on kinematic considerations made earlier by Sommerfeld and Heisenberg. Instead, Kronig found formal solutions in terms of quantum numbers following the lines of Sommerfeld's Gesetzmäßigkeiten approach. And indeed, the same argument was made independently by Sommerfeld and Höhnl in Munich. And as Sommerfeld saw it, the new intensity formulas were a purely formal description which provided a solution to the intensity problem from a practical point of view. Now, developing his purely formal solution, Kronig also considered its relation to the correspondence principle. To do so, he considered the original Sommerfeld-Heisenberg formulas, which were derived from the kinematics of the atom, as we've seen, and expressed them, as others had done before, in terms of quantum numbers using the idea of space quantization. In a separate step, he then factorized his new intensity formulas and obtained from the Gesetzmäßigkeiten approach and found expressions like the ones you see here. From these, Kronig observed that the new formulas could be written as binomials of two different terms instead of the square terms of the Sommerfeld-Heisenberg formulas. These two terms, he thought, were symmetric in the quantum numbers of the initial and the final state. For Kronig, this difference between the original Sommerfeld-Heisenberg formulas and the new intensity formulas was small. Overall, both expressions were remarkably similar. To Kronig, this suggested that the correspondence formulas obtained from the classical kinematics prescribed a general mathematical expression for the intensities. As such, they provided the point of departure for the determination of intensity formulas in more complicated cases. What we thus see here is an integration and adaptation of the original correspondence formulas into the intensity schemes. This adaptation strips the original formulas from their kinematic underpinning and, as Kronig would put it, proceeded half empirically, half on the basis of the correspondence principle. The formal solutions to the intensity problem developed by Kronig bring us to the final point of this talk. Let's consider Pauli's statement from the Handbuch article again in light of the present reconstruction. From the point of view of the original principle, correspondence principle, Kronig's solutions first of all present a challenge. The purely formal description needs to be interpreted physically in terms of the core idea of the correspondence principle. At the same time, this challenge is given in a concrete form which defines the results which the physical approach has to reproduce. By the time Pauli made his statement, this challenge had already become an opportunity. The central assertion of Pauli's statement is that the problem is a purely kinematic one and is independent of the dynamics of the underlying problem. For Pauli, this purely kinematic description did not require a modification of the physical model, but the introduction of a new quantum kinematics. In other words, Pauli was here beginning to think about a new framework for describing motion and not about a refinement of the motion of a particular system. Now, this search for a new quantum kinematics became central in April 1925 during discussions between Kronig, Heisenberg and Pauli, who came to Copenhagen for his Easter vacation. These discussions are hard to reconstruct. From various scattered remarks from Pauli and Heisenberg in their letters, we know, however, that the subject of the discussion had been the general formal problem of calculating transition probabilities. Moreover, we know that this problem was connected with the vanishing at the edges argument, which had become a central principle for the construction of quantum theoretical intensity formulas from classical counterparts. This reconstruction replaced power expressions of the classical intensity formulas by binomials of the quantum numbers of the initial state. Kronig's intensity formulas were presented the simplest, most possible case for this procedure. Here, the classical powers were simple squares, and they were replaced by the products of two zeros at the edges. Now, the last insight into the Copenhagen discussion is given in the very same letter in which Heisenberg developed the multiplication rule of his Umdeutung. In it, Heisenberg famously treated the anharmonic oscillator and tied the resulting expressions for the transition amplitudes to the discussions in Copenhagen. Now, taking these clues together, the following picture emerges. Exploring the intensity problem with respect to the new quantum kinematics, Pauli, Kronig, and Heisenberg considered the anharmonic oscillator and applied the vanishing at the edges argument to it in order to translate a classical into a quantum theoretical formula. This meant a decisive shift with respect to the earlier approaches by Kronig. The study of ever more complicated cases from the zoology of the Zeeman effect were now considered unfruitful. Moving away from these empirically accessible cases, the considerations now focused on models like the anharmonic oscillator as an example for a system that was not restricted by selection rules. These models were seen to provide a formulation of the intensity problem on a general scale. Now, with these conclusions, we are now in a position to reconstruct the considerations in Copenhagen. This reconstruction, with which I will end my talk, show us how far Pauli and Heisenberg and Kronig had come in their search for a new quantum kinematics. As we've seen, the general idea of constructing quantum theoretical intensity formulas makes it necessary to have a classical expression to begin with. For the anharmonic oscillator, such an expression requires to solve the equation of motion. Introducing the respective Fourier expansion of the coordinate x, one collects all the terms associated with the same frequency and arrives at the relations which all have to be zero in order to obey the equation of motion. These relations can be used to determine the Fourier coefficients recursively and lead to a general equation for the Fourier coefficient of the tau of overtone in terms of the overtone A1. Now, this formula is the first necessary step in the vanishing at the edges argument. And the second, far less laborious one, one has to express the Fourier coefficient in terms of the quantum number n of the respective state. To do so, Pauli, Kronig, and Heisenberg considered the simple harmonic oscillator whose frequency and Fourier coefficients are identical with the first term in the series expansion. This approximation makes it possible to determine the Fourier coefficient from the energy of the quantum harmonic oscillator. What you then do in the end is to apply the vanishing at the edges argument and to replace the power expression by the binomial coefficient, which you see here. Now, following this procedure, Pauli, Kronig, and Heisenberg operated with a kinematic description that was still classical and translated their classical solution into a quantum theoretical one. As we'll discuss in our next talk, Heisenberg took the next step in June 1925 and went from a translation of solutions to a translation of the equation of motion. Doing so, he not only considered the same problem, but also approached it in a similar way, obtaining relations between Fourier coefficients and solving the equation of motion. And as you can see down there, he immediately made contact to Kronig's formulas for the multiplets and the Zeeman effect. I want to end my talk by briefly summarizing the main points of my argument. As I've shown, the intensity problem emerged in 1922 as a research problem and was tightly connected to the kinematics of the atom on the basis of the correspondence principle. In 1923 and 1924, the intensity problem was then reformulated within Sommerfeld's formal Gesetzmäßigkeiten approach, and this reformulation cut the ties with the underlying kinematics and presented, therefore, a challenge to the correspondence approach. This challenge was answered by the Copenhagen community in 1925. First, Kronig integrated and adapted the original correspondence formulas into Sommerfeld's formal schemes, and then Pauli and Heisenberg and Kronig later aimed to recover their kinematic interpretation. This attempt was directly connected with the search for a new quantum kinematics. If this is convincing, I think Sommerfeld's Gesetzmäßigkeiten approach played a much more central role in the development of Heisenberg's work than has hitherto been assumed. Heisenberg's Umdeutung was both a reinterpretation of classical mechanics into quantum mechanics, as well as it was an interpretation of the formal classification of spectral data in terms of a mechanical framework. As such, it combined both Bohr's thinking about the correspondence principle as a rational generalization, as well as Sommerfeld's search for Gesetzmäßigkeiten. Thank you very much.
Thank you so much. So let me see. Michelle?
Thank you, Martin. That's really like a beautiful talk about unearthing these developments. I have a lot of questions. I want to. Yeah, I'm thinking that it may like throw light on things that are puzzled, that have puzzled me for a long time. So let me ask you, like, there's another thing. So the sum rules, right? So I always noticed that Black, like in the 32 book, like he's talking about this principle of spectroscopic stability, which apparently like played a big role, but like in the way I think about it, like it's very hard to place it. This way of thinking about it, does that throw light on what is meant by this principle of spectroscopic stability?
Spectroscopic stability, as far as I can understand it, is the polarization rule. Sort of the idea that if you have an unresolved parent line which is not polarized, then if you split it up, then the sum over the individual components also has to have a non-zero polarization.
So that is different from the sort of...
That's the sum rules and the polarization rules are equivalent in a case where you can actually say something about the polarizations, which is the case in the Zeeman effect, while at least in the period we are talking about, the same cannot be said for multiplets.
Let me ask you one other question about like another aspect of this. So there's this article by McKinnon, right, on, I'm sure you're familiar with one, and where McKinnon actually got a reaction from Heisenberg. And but McKinnon also claims that like this paper on the Zeeman effect played a very important role. Tell me how they were able to see how this works. Looking at multiplets, right?
Mm-hmm.
So looking at the strand that you're looking at, does this communication between McKinnon and Heisenberg now fall into place as well?
Well, as I see it, the McKinnon story certainly falls into the strand and it's directly connected with the bit which I left out on Heisenberg's sharpening. Because sort of before these formal solutions by Kronig arise, Heisenberg has an intense argument with Pauli in a series of letters where they discuss sort of how you can save the correspondence principle physically using virtual oscillators. So, and the trick is you have to go over from Zwischenbahn to attaching to saying your virtual oscillators are actually connected to the initial state of the atom, to its Fourier series. And this is also what happens sort of in these Kronig formulas. They are also expressed in terms of quantum numbers of the initial state. Now what happens if you use the Zwischenbahn model is if you have, as long as you have individual components, you're fine. But if you have like a ratio with these angles in it, as soon as you get different Zwischenbahn for the transitions from one initial state to 3 different final states, of course, these trigonometric terms will never add up to 1. So that essentially kills the Zwischenbahn model. And the only solution is to say, well, we are going to deal with one orbit and one inclination with respect to an external field. So, but to just say one more thing, I think this clinging to the notion of virtual oscillators on which McKinnon places so much trust, I think I've shown that this is not the case. It's about, first of all, getting this formal structure right, and then taking a step back to discover the kinematics underlying it. But the model of the virtual oscillator does not play a role in it, I think.
Okay, Jora?
Thank you. I think you mentioned, is it 1922, the first expression of the correspondence principle that you quote?
Well,
is it
the
22? My question actually concerns the prehistory of that.
Mhm.
Do you see some kind of suggestions or vague expressions, but in this direction in Bohr's writings earlier than
Of course.
1918? It's 1918.
Well, the correspondence principle in Bohr's formulation sort of dates back to 1913 and then transforms around between 1916 and 1918 into the form which I quoted. But initially, Bohr does not formulate it as a principle, but is giving an argument. The funny thing is, as early as 1919, physicists start recognizing and actually denoting this as a principle, as the analogy principle, or interchangeably as the correspondence principle. So there's an odd thing about this about the reception, which just remains, because Bohr only starts talking, to my knowledge, about the correspondence principle as such in 1923, and that's what the formulation which I gave you here, that's where it comes from. Sorry.
But do you recognize a deep change, or is it some kind of explanation or extension of the idea, the earlier?
Well, it's a transformation from 1913, where sort of Bohr already tries in the classical limit to recover the connection between radiation and motion, but then he uses it essentially to quantize the motion of a state, whereas he will later on use the principle to govern the possibilities of transition. That's the essential translation which comes about, and this is what then will become the central point from 1918 to 1925 and beyond that.
Okay, so first I put myself on the list. I have a short question, very general. You showed these tables that were being done in Utrecht, yeah? And
no, they were done both in Utrecht and by Sommerfeld in slightly different but identical ways. I can put one.
But no, for me it's interesting, this table form, because of course in Heisenberg's work the key point was these functions of the two quantum numbers, initial and final state, which is quite reasonable if you're doing transitions. And so this is the first time that I saw, this is from the original paper, really?
This is from Sommerfeld, Atome und Spektralien, the fourth edition, and you would find it in Burger and Dorgelo earlier with a slight modification. I mean, so in the Burger-Dorgello form, it's where the statistical weights are down there.
Before matrix mechanics or after? Because
that's way before. That's 1923.
Yeah, and do you think that could be some such? I mean, from the purely visual element of this formalism.
Well, I think it would be. To put it with Van Vleck, it would be tempting but probably futile to interpret this as a pre-notion of matrices.
Not a pre-notion, but, well...
But what I do see, and what I try to hint at, is that Heisenberg's formulation that will lead into matrix mechanics is essentially recovering this formal structure which is laid out here.
Exactly. No, thanks.
And just to make another point of it, Helmut Höhne is going to develop these kinds of things throughout 1925 and not go beyond the Gesetzmäßigkeiten approach. In the end, he will, however, reflect on these formulas which come out and be very puzzled that he has products involving the initial and the final state. But he doesn't go beyond that. And he compares it a bit with what you do for frequencies, but that's it. And that's how far the purely Gesetzmäßigkeiten approach gets you, I think.
Okay, thanks. Arne?
Just a quick question. In your reconstruction, you stressed the role of Sommerfeld's Gesetzmäßigkeiten, of the Copenhagen discussions. And you concluded that this clearly fueled the search for a new kinematics. I just wondered, did Göttingen play any role?
Well, as far as I've been able to reconstruct it, because we do not have a lot of letters from Born on this subject, the Utrecht sum rules, I didn't find any evidence how much they were discussed in Göttingen, and they certainly do not play a role in the papers we have from this period. So they were probably known, but a detailed discussion of them I don't see at the point, because Born is not really into these spectroscopic classifications, and the one who is, Friedrich Hund, does not become a player in this game which we're talking about.
Great. More questions? If not, then thank you so much.